Welcome back. So in our last video, we developed the idea that logarithmic functions are inverses of exponential functions. So we'll state that formally here. The logarithmic function y is equal to log base b of x. It is the inverse of the exponential function y equals b raised to the x power. And remember that the base is not going to equal 1, and the base must be positive, so the base must be greater than 0. So therefore, if we can remember the common features of an exponential graph, then when x and y are interchanged, which is what we do to create the inverse, we'll easily be able to come up with a list of features for logarithmic functions as well. So for example, when we're talking about parent functions, y equals b to the x, before any shifting and before any reflecting, we know that these exponential functions will have a y-intercept of the point 0, 1. So if x and y are interchanged, then that means that our logarithmic functions will have x-intercepts of the point 1, 0. And again, we're talking about the parent functions, so before any shifts and before any reflections or stretches. Then remember, when we're dealing with domain, we're looking at all of the possible inputs. So what am I allowed to put in for x? And for an exponential function, I can put in any type of number. So the domain is all real numbers. That would be negative infinity to positive infinity. And if the domain and range are interchanged, which is the same thing as saying the x and y values are interchanged, then that means that the logarithmic functions will have a corresponding range of all real numbers as well. Then the range for those exponential functions, because they have horizontal asymptotes, the range was from 0 to infinity. That's the y value, or y values. So therefore, those become the x values for the log functions. So the log functions will have a domain from 0 to infinity. And let me pause there and really make note of that. Remember, the domain is all the possible x values, and for a log function, x is what we call the argument. It's the input, and that means that we are only allowed to input positive values in logarithms. So we've noticed in past videos that we can't take the log of a negative and you can't take the log of 0. And so that confirms that our domain here should be from 0 to infinity for all of those log functions. And then the last commonality will be the asymptotes. So exponential functions have horizontal asymptotes, and the parent functions always begin with a horizontal asymptote of y equals 0. Therefore, that turns into a vertical asymptote for a log function, and that will be the vertical asymptote x equals 0. So next, let's use these commonalities and let's discuss how to graph logarithmic functions. We're going to graph two of these and kind of compare them side by side. So the first function we're graphing is y equals log base 3 of x. And notice my hint for you here, because it's an important one, that when we're graphing any logarithmic function, it always helps to rewrite the equation in exponential form first. We're going to do that every time we graph a logarithmic function. So I'm going to start by changing this into its exponential form, which would be 3 raised to the y power is equal to x. And then I'll just make a table to graph this. Remember, making a table is always our primary method if we don't have any other method at hand. And we typically fill our table from -2 to 2. However, look at the equation 3 to the y equals x. It would be much easier for us to choose y values rather than choosing x values in this case. So I'm going to actually fill up my table from -2 to 2, but I'm doing that on the y side to make these computations easier. So we're going to substitute in -2 for y. So that's 3 raised to the -2 power. And I'm showing my work here. I would hope that you can do this in your head at some point, hopefully. We'll work towards that. 3 to the -2 power. The negative exponent makes that 1 over 3 to the second power, which gives us a value of 1 over 9, 1/9. Inputting 3 to the -1st power, We're inputting -1 for y. That will become 1 over 3 to the first power, which gives us a value of 1/3. Then 3 to the 0 power will be 1, 3 to the first will be 3, and 3 to the second will be 9. So let's plot these values and then see if we see the common features that we just developed above. So 1/9 -2, that's going to be difficult to plot because it's so close to the x-axis. 1/3 -1, kind of same thing, you're just going to estimate those. Then we see 1, 0, we have 3, 1, and we have 9, 2. So notice this graph is going to hug the y-axis and then grow in the opposite direction. So we indeed do see that we have a vertical asymptote here. I always like to do my asymptotes in a different color. A highlighter works nicely as well. So we've got a vertical asymptote of x equals 0. Notice that common point of 1, 0, that's the x-intercept. And sure enough, it does indeed have the domain and range that we expected. So let's fill in those values below. We have that asymptote, which was a vertical asymptote of x equals 0. A domain, which is from 0 to infinity. A range, remember the y values, it goes down, this graph goes down forever. It also is increasing forever, so we have -infinity to +infinity, and that common x-intercept of 1, 0. So these 4 common features indeed show up on this graph. Now let's go over here and do the same thing for y equals 1/3, log base 1/3 of x. So we'll start in the same way by rewriting this equation in its exponential form. So 1/3 raised to the y power is equal to x. We'll make a table for that. Once again, noticing that it would be much easier to choose y values, so we're going to input y values in our table from -2 to 2. So I'm going to show my work over here, 1/3 raised to the -2 power. That negative exponent is going to end up basically flipping this fraction, so the 1 will go to the denominator and the 3 will go to the numerator. And let me just mention why that is again, because that negative exponent really is going to make this 1 divided by 1/3 squared. But we know when we divide fractions, we change it to multiplying by the reciprocal. So, 1 divided by 1/3 squared is 1 divided by 1/9, which turns into 1 times 9 over 1, which is why this ends up being 9. But many times we don't show all this work. We just realize that that negative exponent will flip that fraction. 1/3 will turn into 3 over 1. That will be squared, which indeed gives us a value of 9. So now inputting -1, 1/3 to the negative first power. Again, the negative exponent is going to flip that fraction. It turns into 3 over 1 to the first power, which gives us a value of 3. 1/3 to the 0 is 1. 1/3 to the first is just 1/3. And 1/3 to the second is 1/9. So we'll plot those values. 9, -2. It's a nice easy one to plot. 3 and -1. 1, 0. And then the 1/3 1, you'll just estimate, and same with the 1/9 2. So this time, the graph is still hugging the y-axis. However, this is not an increasing graph, this is a decreasing graph. So let's look at those common features one more time. We see that nice vertical asymptote we expected, vertical asymptote of x equals 0. And there's that common point of the x-intercept 1, 0 as well, which we had expected from earlier. So we'll fill in these features, the vertical asymptote, x equals 0, domain from 0 to infinity, range from -infinity to +infinity, and x-intercept is 1, 0. So in the future, when we graph our logarithmic functions, we can really use these features, these commonalities, we might find that it's helpful to go ahead and graph the vertical asymptote in first, and maybe even graph the x-intercept first. And then the last thing I want you to notice before we finish here is when the base was 3, this graph was an increasing graph. And when the base was 1/3, the graph was decreasing. So that tells us that when the base is greater than 1, the graph is going to increase. And when the base is a fraction between 0 and 1, the graph will decrease.